Okay, so we had these original data points, the red point and its original coordinates of length, weight, and width, and the blue point. And we expressed it in a different basis, namely using axis 1, axis 2, and axis 3, and the coordinates along those vectors. And then we just set those third coordinates equal to 0. The rationale for that will be exposed later, but for now, just trust me, we just wanted to get rid of that axis, which left us with a simpler expression where we had the red point and the blue point were approximately equal to a linear combination of 2 of those axes. Now, why approximately equal to? Well, because there was a third term over here that we chopped off. So now what I'm going to do is I'm just going to replace these placeholders of axis 1 and axis 2 with the actual axes from above. Okay, so you get a more clear picture of what's actually going on in this sum. And now we can use what we know about linear algebra to rewrite that linear combination as a matrix vector product in both instances. Okay, so I've just rewritten the expression so that it's a matrix vector product rather than a linear combination. And now, keeping in mind that the other things that I know about matrix multiplication, I don't have to keep these as 2 separate expressions, because the way that matrix multiplication works is that in order to get the first column of the result, I can think about that as multiplying the first matrix times the first column of the second. Okay, and in order to get the second column of the result, I multiply the matrix times the second column. So we'll put some labels on this. This matrix on the left here, well, that's my data matrix. That's just 2 observations. Granted, the observations are in columns here. Again, mathematicians love to think about their objects of interest as column vectors. So the only thing that's different here than what you're conventionally used to is that I've put my observations along the columns and then my variables, length, weight, and width, along the rows of the matrix. If you'd like to transform this into your conventional statistical framework, you just transpose both sides of this equation. But for now, I think it's a little bit easier to see using the matrix as columns. All right, and then on the right side of the equation, I have factored my data matrix into the product of 2 matrices. The first contains what we call the latent factors. The word latent means hidden. So these factors are driving forces that were hidden in my data until I did this procedure and I uncovered them. Okay, we labeled those latent factors as size and weight. And then I have a matrix of scores. Again, these are just the coordinates of these data points in the new axes, which again are the bold, darker straight line arrows here. So x11 told me how far to go along the black arrow I'm pointing to now, how far to go along axis 1. x21, wiggle, sorry, these are the wiggle numbers, it's the new numbers, showed me how far to go along the second axis. So they directly reference these new factors, and I can conclude from them that x11 must be a big number, meaning that the red point has a larger size than the blue point, and x21 has a smaller coordinate along this second basis direction, meaning its weight is smaller than the blue point. Now, you may be a little uncomfortable with my labeling of these latent factors as size and weight. Good for you. It's good to challenge new ideas when you hear them and they're fuzzy, because all I did was say, well, this number here, 0.89, is the biggest number in the vector, And this number, 0.45, is also the biggest, or the second biggest number. And both of these numbers are big compared to the middle number. And therefore, I'm going to ignore the middle variable and attribute this axis 1 the qualities of length and width. That is how it became size. So yes, I agree with you, that is a little fuzzy, but I promise you that soon as you see more and more examples of this, you'll become more comfortable with the idea. Because while there is room for a little subjectivity, there is a notion of truth that generally comes up to the surface. And you'll see that in the next example, I think. All right, well, that's all I wanted to say for this here. Really just hitting home this idea that this change of basis gives us a matrix factorization of our data matrix. And you'll see a more concrete example of this in a higher dimensional space. I think one of the reasons why it's so difficult to really get what's going on here is because we're trying to do it graphically and it's only in 3 dimensions. So it just seems a little pointless. And you're right, it is. We don't do this in 3 dimensions. So let's see it in a higher dimensional space next.